Yeah, go. While you're getting donuts, I'll just start with today's material. So this is it. This is our last lecture. Okay, our final exam is scheduled for next Wednesday, a week from today. We do not meet on Monday of next week, right? It's finals week, so we won't meet. Our exam starts at 9 a.m. Be here on time. Goes till 11:45 a.m. So almost 3 hours right here. Bring with you all the formula sheets that I provide to you on Canvas that you probably have been using already all semester. Bring those. In addition to that, of course, your calculator, pencils, all that stuff. I'm allowing you one reference page, one cheat sheet, front and back. You can write pretty much anything you want on there with the exception of working out problems and putting it on there. So you can have additional notes, formulas that you know that aren't on this sheet, or just if you want to kind of summarize ideas, procedures, concepts, you can do that. Tricks, whatever you want, things to look out for. What I would do if I were you is I would take a look at that review, and then as you're doing the review, kind of say, oh, you know what, I needed this and I didn't have it, so let me put it here. So yeah, that's the plan. Okay? So next thing, we're going to get right into we started chapter 8, section 7, Taylor-Maclaurin series last time, and I was really rushing at the end. So I'm just going to summarize what we did. Basically what we said is, a generic power series, if we're given a generic power series, assuming that this thing actually has some sort of radius of convergence which is greater than 0. In other words, this is defined on some interval or the entire number line. As long as that's the case, then we went and tried to see if we could find a formula for the constants. And we said, you know what, there's a way we can get this formula, perhaps, if we can do this, right? So I derived this for us last time, that what we're trying to do to find the formula for this is we need to be able to find a formula for the nth, this stands for the nth derivative, the nth derivative of the function at a is this number, right, at a, and then divide that by n factorial. That is the formula for c sub n. And if we can do that, right, if it's possible for us to do this, because we'll have to take a bunch of derivatives and try and find a formula, if we can do it, then we have these two new, names for series when we look at them from this perspective of not putting c sub n here anymore. By putting that formula, we have what's called the Taylor series at a, at x equals a, and that's our c sub n replaced with that formula, right? And then this is x minus a to the n, that's the same thing, right? So that's your Taylor series centered at a. Now, you also have this thing called a Maclaurin series, and all a Maclaurin series is a special case of the Taylor series where x is equal to what? Where x is equal to 0. Okay? So if you take the Taylor series and you replace all your a's with zeros, this becomes the nth derivative at 0. Oh, sorry, that's 0. The nth derivative at 0 over n factorial, and then this is still this, right? But a is 0, so this is just x to the n. So the Maclaurin series is a power series centered at 0. A Taylor series is centered somewhere else. That's all the difference is, all right? So with that, we are going to get into our first real example. I started an example last class, but I'm going to start over. Please break out that sheet that I had that says how to find Taylor-Maclaurin series. Anybody need that? Everybody have it? So here's the deal. When we're going to try and find this formula right here, okay? We're going to try and find this formula. And when we do it, really one of two things is going to happen. Either we're going to be able to find the formula, and we're going to be super happy about it, or the formula is going to be really hard to find. So what we're going to have to do is actually just write out term by term what we're getting for these derivatives and write out the new series. Just write it out. And then once we look at that written out series, we're going to try and come up with the formula from that. So just let this play out, okay? But this gives you the instructions on how to do it, all right? So I'm going to follow this. In fact, I'll bring it up here. Where is it? Sorry. Okay. All right, so let's do our example here. So the example we want to start with is e to the x, all right? So what I'd like to do right now is find the, what was the answer? Maclaurin series, I think, yeah. I want the Maclaurin series for e to the x. They're donuts, if you're interested. I didn't bring them. Chris brought them. But he gets, yeah, see, he doesn't have to take the final. He gets an A in the class. Congratulations, Chris. Good job. Okay, so here we go. Y'all ready? Find the Maclaurin series. So find the Maclaurin series for f of x equals e to the x. So this is what I was getting at when we first started talking about chapter 8. The whole point of chapter 8 is, can we take a function and represent it in a different way, which will make hard problems easy. So e to the x, we're going to go ahead and see if we can find the Maclaurin series. So what does it say here? First thing, I want to make a table. I want to start making a table of all the derivatives of this thing. All right, just start listing out the derivatives, which should be easy, right? So here we go. Here's my table. And so what I'm doing is the step 1 right now. Step 1, make a table of the derivatives. So the way I write this is first the 0th derivative of this function, which just means the original function, e to the x. Then I take the first derivative, which is itself, right? First derivative, which is just itself again, right? And then the second derivative, and that's itself. I think I can stop here, right? I keep going down. What is the nth derivative going to be? Itself, right? E to the x. Great. Okay, that's just me getting the derivatives. Now I move to step 2. Since I'm doing a Maclaurin series, now what I want to do is I want to evaluate these derivatives at where? 0. X equals 0. Why? Because I'm asking for Maclaurin. Maclaurin is when x is 0. So we're centering this thing at 0. So when I take this and I take that 0th derivative and I plug in 0 into it, I get e to the 0, which is 1, right? And that's going to happen for every one of these, isn't it? Every single one of these, I'm going to get 1. Even down here, this final one, the nth derivative at 0 will be e to the 0, which is 1. And what I want you to see, and this is a part that students tend to mess up, is that what we have found here, right here, we have found the nth derivative at 0, right? Right there, the nth derivative at 0. And we said that that's 1, right? So if you come back over here to the Maclaurin series formula, we have found this part right here, just that part right there. That's 1 for us, isn't it? We still have to divide that by what? N factorial. We can't forget that. The n factorial is something we have to add in once we find that formula. We have to divide by it. So here I go. Here's my Maclaurin series. So the Maclaurin is going to be, I'm going to start writing this out, sum n equals 0 to infinity of, this red box was 1 because we were able to find that pretty easily, 1 over n factorial, and then x to the n. And that is it. That is your Maclaurin series for e to the x, which we can start writing out some terms. Let's just write some out just so we have them. If I start writing them out, if I plug in 0, I get 1 over 0 factorial x to the 0, plus now plug in 1 over 1 factorial x to the first power, plus 1 over 2 factorial x to the third power. What am I doing? 2, right? Plus 1 over 3 factorial x to the third, plus, keep going, right? And I can clean that up a little bit, maybe. What's 0 factorial? 1, and then x to the 0, 1. So this is 1 plus, okay, what's 1 over 1 factorial? That's 1. 1 over 1 is 1. X to the 1 is x. So we just get 1 plus x. And then plus, this next one is x squared over 2 factorial. 2 factorial is 2, but I'm just going to write it as factorials from here on out. And so on and so forth, right? Plus dot, 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 that goes forever. Okay? Now, did anyone happen to bring one of the sheets from online that has the series? It's sideways. It has the Maclaurin series on it. Anyone have it with you by chance? Yeah. You're allowed to have this on the test. Yeah, can you pull that out real quick? So there's a sheet on the web in Canvas under Files that has all the Maclaurin series for a lot of the common functions. All right, and if you look at this one, the second one down, okay, the second one down there is the Maclaurin series for e to the x, which we just derived. Okay. Now we move on. I have a lot I want to do today, so let's see. Example 2. Let me make this bigger. Look at what it says. Use your answer from example 1, which we just did, to find a new expression for e. To find a new expression for e. E, just e, right? Do you all remember this? Do you all remember earlier in this class, and this happened in Cal 1, there was this special limit n goes to infinity of 1 plus 1 over n to the n. That was this really weird limit, but I said, does anyone remember this from Cal 1? And then we determined that this limit is actually e. And I said, you could actually define e to be that if you wanted to. Well, what I'm asking you to do is use this answer to represent e a different way. So that's just to make you recall. We've defined e already in this class a certain way, but here's a new way to define it. E is just e to the 1, isn't it? E to the 1. And this right here, this series that we found just now, this right here, this is e to the x, isn't it? That's e to the x. So if I just replace all my x's with 1s, right, then that's what e to the first power would be. So what is e to the first power according to this? 1 plus 1 squared, 1 over 2 factorial is 2 plus 1 cubed over 3 factorial plus 1 to the 4th over 4 factorial plus forever and ever, right? Forever and ever. If you got your calculator out right now and did 1 plus 1 plus 1/2 plus 1/6 plus 1/24, I'm going ahead and I'm writing out what these factorials are, right? 2 factorials 2, 3 factorials 3 times 2 times 1 is 6, 4 factorials 4 times 3 times 2 times 1, which is 24, right? If you were to get your calculator out right now and start adding these up, 1 plus 1 plus 1/2, your number is going to get really close to 2.718, which is what e is. Okay? And the further you go, the closer you get to that answer. But of course, e is irrational, right? It goes on forever. There's no pattern. How could you get more and more decimals for e? You just go further and further down the series. Okay? All right, good? Let's move on. Example 3. Now what I want is to find the Taylor series, not Maclaurin, the Taylor series for e to the x at x equals 2. So this is different now, right? This is different. So we're going to follow the procedure. The procedure is on the back of this. This is how we find Taylor series on the back page, right? We're still going to make a table of derivatives. I'm going to do it over here. Do it right here. So I'm going to make my table of derivatives first. The 0th derivative is itself, right? And then I'm not going to do this. We just did this, right? We know that the nth derivative here is e to the x, right? This is like the easiest function to do a series on because the derivative is itself, right? But now what do? The second part of this says now I'm going to take that derivative and plug in what? Plug in a. What's a for us? 2. So what would I get? E squared. And that would be for each one of these, right? For every one of these, it would be e squared, e squared, e squared, all the way to the bottom. So the nth derivative at 2 will be e squared. You all right with that? Now, we found a formula for the nth derivative of that function at 2, right? That is going to be our Taylor series. That is this piece right here. It was 1, right? When we did Maclaurin, it was 1, but now it's what? E squared. So we're going to have an e squared here over n factorial, and then over here we're going to have what? X minus 2 to the n. And that will be our Taylor series. So our final answer here is sum n equals 0 to infinity, e squared over n factorial, and then x minus 2 to the n. Now, I'm sure you're asking, like, what's the difference, or you're thinking maybe, what's the difference between Maclaurin and Taylor, right? Well, it all has to do with the convergence. So we already talked about power series either converge. There's 3 cases, right? At a point, at an interval, or the entire number line. We'd never look at power series at a point because they're useless functions, right? A function only defined at one point. So we're really more concerned with if it's defined on an interval or in the entire number line. If the series is defined on the entire number line, y'all listening? If it's defined on the entire number line, if your radius of convergence is everything, you never need a Taylor series. You never really need this because your series is going to converge everywhere. You don't have to be looking in a window for it to work. So you don't need to do a Taylor series because a Taylor series, the minus a, all it does is it shifts the series left and right. So because if we're looking at something that converges everywhere, you just use the Maclaurin. But if this series has some interval of convergence where it's only valid in this little window, then you may need a Taylor series to move to the right window so it works for what you're trying to do. I hope that makes sense. Turns out for e to the x, it converges everywhere. So all we ever need is the Maclaurin. Okay, let's keep going. Next example. Find the Maclaurin series. Maclaurin, right? Maclaurin for sine x. This is what I tried to start last class. All right, series for sine x, right? Right, this one's going to be a little more complicated. Here we go. So I start taking derivatives, right? 0th derivative itself. First derivative, so, for me, it gets a little bit cumbersome to do this like over and over and over, write f with the derivative mark. So what you can do instead of this, if you want, you don't have to, is you can do something like this. Let me just erase this completely. I'm just going to put like derivative here, right? Derivative 0th, 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, right? And then just start looking at the function. It was sine x. What's the first derivative of that? Cosine. What's the second derivative? Negative sine, and then negative cosine, and then sine. You'll see what I'm doing? Instead of having to write that, f, 3rd derivative, 4th derivative, it's just kind of a pain in the ass. So derivative sine is cosine, derivative cosine is negative sine, derivative negative sine is negative cosine, derivative negative cosine is back to positive sine. And now it's cyclical, right? We have a cycle. It's going to repeat itself, right? So cosine, negative sine, negative cosine, and then back to sine again. Do you see the problem with me trying to tell you what the nth derivative is? We're not sure what n is, right? So we're trying to come up with a formula for the nth derivative, but I know that the nth derivative can be what? One of 4 things. it's either going to be sine, cosine, negative sine, or negative cosine. I don't know which one it is because I'd have to actually tell you what n I'm referring to, right? So do y'all see it's going to be hard for me to actually come up with the formula for nth? For the nth, question mark. I don't have an easy answer for you. See how this contrasts with the e to the x? Okay, well, let's not freak out. Let's do the Maclaurin now. Let's do the second part of trying to find Maclaurin, which is to plug what into the derivatives? 0. So again, I'm just taking each one of these and I'm replacing the x with 0. Why? Because we're doing Maclaurin. All right, so what's sine of 0? 0. Okay, now this one. Cosine of 0. 1. Negative sine of 0. 0. Negative cosine of 0. Negative 1. And then it's going to what? Start repeating itself. So it'll be what? 0, 1, 0, negative 1, 0, 1, 0, right? That's what it's going to keep doing? So can you give me an nth? Can you give me a formula for the nth derivative at 0? No, right? Again, it's going to either be a 0, 1, or a negative 1. Do you see the problem I'm having? I don't have an easy way of representing an nth answer, right? The nth derivative at 0 is a question mark for me. So how do we work around that? So if you look at this, right, the handout, I said do one of these, step 3, do one of these. If it's possible to easily find the formula, just plug the formula in, right? Boom, you're done. But if you can't, then what you're going to do is you're going to write out this series. Okay, you're going to write it out. So if I plug in 0 here, it'll be the 0th derivative at 0 over 0 factorial, x to the 0, plus, and then what? The first derivative at 0 over 1 factorial, x to the first power. Do y'all see that's what I have written out here in blue? All those numerators? That's what we're going to do. We're going to write this thing out. All right, so I'm going to erase this. So here's what I'm doing. I'm saying that this series, sum n equals 0 to infinity, the nth derivative at 0 over n factorial x to the n. I was never able to find a formula for that, right? I was never able to find a formula for that. However, if I start writing this out, it'll be, do I need to write it? You have it in blue right there, right? You have it in blue. So I'm doing the 0th derivative, sorry, the 0th derivative at 0 is the first one, right? Can you all tell me the 0th derivative at 0? What is the value? It's this one right here, right? That is the 0th derivative evaluated at 0. So I get a 0 over what? 0 factorial x to the 0. That's my first term, which will just turn out to be, it'll be 0. Plus, okay, now I'm going to plug in a 1 here. So I want the first derivative at 0. What's the first derivative evaluated at 0? Is 1, right? So I have 1 over what? 1 factorial x to the 1. Now I plug in 2. Have a donut, man. No? You want a donut? Oh, I didn't say you weren't. There's a bunch of up here. Everybody, there's donuts. You want me to pass them around? You're looking at them. Here we go. Here, pass them around. Pass these around. Here's napkins. Okay, what's next? Plugging in 2, right? The second derivative at 0. Okay, here's my second derivative. When I plugged in 0, I got what? 0. 0 over, I'm on the second one, right? 2 factorial x squared. Now, plug in 3, right? Third derivative at 0. Here's my third derivative. Plug in 0. I got negative 1. Negative 1 over 3 factorial x to the third. Y'all see what I'm doing? I wasn't able to come up with a formula for the nth derivative at 0. I couldn't come up with a formula, but by doing this, I'm kind of just at least writing out the series, right? Now, I'm not even going to look at this anymore. Well, I guess I am. I know that now it's just going to be cyclical, though, right? So when I do the next one, I'm going to get the 0, the same 0 I had here, 0 over 4 factorial x to the 4th. Plus, then it's going to be a 1, right? 1 over 5 factorial x to the 5th. Plus 0 over 6 factorial x to the 6th. Plus, what's next? Negative 1 over 7 factorial x to the 7th plus dot, 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 right? I'm going to stop there. Questions on that?
Would you only do like this is a cyclical addition, you just do it to like the point where it repeats itself over?
I think what we have to do, this is not our answer. We have to find a formula. We have to find a formula to be done. So you want to go out as far as you can to be able to get the formula. Yes?
So, like, let's say we're doing this test.
Yeah.
Do you recommend, like, do we have to do it again to repeat? Like, can we stop at third? Like, that's where that, like, you know, we stop.
If you think you can get the formula from this, then you can stop here. See, let me get the formula first, and then maybe you'll see what I'm talking about. So here's what I'm going to do now. There's a bunch of these that are just zeros, aren't there? Look, this has a 0 up here. That's gone. This is gone. This is gone. This is gone, right? All those are gone. So let me write what's still here. I have 1 over 1 factorial x to the first power minus 1 over 3 factorial x to the third power plus 1 over 5 factorial x to the fifth power minus 1 over 7 factorial x to the seventh power plus dot, dot, dot. Do you see that what I did is I used that negative that was up top and I just made it a minus out front, right? Now look at that. Can you come up with now the sigma notation for that series? Starting at 0. Okay, so let's take a look at what's happening. First of all, it alternates. Starting with a positive, then negative, positive, negative. Can you make that happen?
Yes.
How? Negative 1 to what power?
N plus 1.
You can do n plus, careful, where are we starting? You have to make sure I'm not saying you're wrong. I'm just saying make sure you look at where you're starting. N is going to start at 0, right? So if I just put n here, what would happen? That'd be positive 1, wouldn't it? And then the next time I plug in n equals 1, it would be negative 1. So wouldn't this make it alternate?
Yeah.
Yes? Starting with a positive. Okay, what else do you notice?
It's over N. Plus 1.
This is all over, let me move it a little bit. This is negative 1 to the n. It's all over, okay, each one of these is 1 factorial, 3 factorial, 5 factorial, 7. Those are all odd numbers. Starting with 1. Create a list of odd numbers starting with 1. Careful, n starts at 0. 2n, because they jump by 2 each time, but you need to start at 1, so plus 1, all of that factorial. Right? If I let n be 0, what do I get here? 1 factorial. If I let n be 1, what do I get? 3 factorial, right? Do you see that's going to get us what we want? Almost done. You have x to the first, x to the third, x to the fifth. That's the same odds, isn't it, as the factorials? So I'm going to say times x to the 2n plus 1. That's it. That's your Maclaurin series for cosine. If you look on that sheet, that sheet that I just held up, pardon? I'm sorry, did I say cosine? I'm sorry, I meant to say sine. And I mentioned to you all last class, or the class before, that if you look at sine, right, if you look at the sine function, you think back to pre-cal, when you learn about the sine function, they tell you sine is an odd function, right? And I told you already that the reason it's really odd is because its power series contains only odd powers of x. That's what makes it an odd function. All right, you ready? Cosine's next. So we're going to find Maclaurin for cosine. It's going to be very similar, isn't it? In the sense that we shouldn't be able to find a formula. Like, we shouldn't be able to do a formula down here with cosine, because we're still going to get some sort of alternating. Let's do it. All right, so what's the zeroth derivative of cosine? Itself, right? First derivative, negative sine. Second derivative, negative cosine. Third derivative, sine, right? And then back to cosine. You're all okay with those, right? And we will not be able to come up with a formula for the nth because it's switching. Okay, next. What do I do now? Plug 0 in, right? I'm getting the Maclaurin, so I'm going to let x be 0 into these. And I'm going to get 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0. Got it? It's the same sort of repetition we had before. It's just starting at a different place, isn't it, this time? It's shifted over, exactly. If it's shifted over, we're not going to get odds. We're going to get even powers, right? Which is why cosine's an even function. Any questions before I proceed? Okay, let's do. If n is 0, we want the 0th derivative at 0. 1. 1 over 0 factorial x to the 0. And then plus, now let n be 1. So we want the first derivative at 0, which is 0 over 1 factorial x to the first. And then plus, now we're ready for 2 to be plugged in. The second derivative at 0, here's my second derivative at 0, is negative 1 over 2 factorial x to the second. So I was asked earlier, where do you stop, right? Well, is this enough for you to get the pattern? I don't know. That depends on you. I mean, do you feel like you have enough? Look, this is what's going to go away. That one's going to go away, right? So you're going to have 2 terms to create your formula from. Is that enough for you to create it? I don't know. I mean, I know what the answer is, so I know that's enough for me. But maybe you need a few more just to verify that you're doing the right thing, right? So am I answering your question about how far to go?
Yeah.
Yes? I'm sure that wasn't very convincing yes.
But if you would stop at the next one, that's like kind of
Well, the next one's going to go away, though, right? So it's not going to help you in any manner, right? Like the next one's a 0. So maybe one more after this. So what would be the one after this? What would be the, where are we, 4?